What if the Big Bang wasn't the beginning? Not the start of everything, but a transition? And what if, before that transition, the universe already had structure? Not made of matter, but made of geometry. In standard cosmology, the Big Bang is where everything begins. Space, time, matter, and energy all emerge together. But there is a hidden assumption in that picture, that the geometry of the universe is fully described by curvature alone, that everything reduces to how mass and energy bend space-time. That assumption can be relaxed. Geometry may have more than one degree of freedom. In a non-minimal Poincaré gauge framework, space-time does not just curve. It can also twist. That twist is called torsion. Curvature is tied to energy and mass, while torsion is tied to spin and angular momentum. Not just local spin, but potentially distributed angular momentum, carried across the geometry itself. Now shift one assumption. What if time is not a thing in itself, but an ordering of configurations? Then the Big Bang does not have to be the beginning of time as a substance. It becomes the earliest configuration in the ordered sequence that defines our observable universe. Time, in that sense, is just the indexing of change across that sequence. The question then changes. It is no longer about what came before in time, but about what geometric structure is present in the configuration immediately preceding the transition. Rather than invoking separate universes, consider a single geometric domain, a proto-geometric manifold. Within it, there can be high-energy restructuring events. These events can be of the same kind as the Big Bang associated with our observable universe. We refer to earlier instances as proto-Big Bangs to signal their position earlier in the ordered structure. There is a single underlying ordering of configurations. What we refer to as the sequence of a Big Bang is not a separate sequence but a segment of that ordering, viewed as a continuous macroscopic regime. Time in this context is simply the local indexing of that ordering within a given segment. Each proto-Big Bang defines its own reference point, so the indexing begins differently depending on which segment is being described. What differs is not the ordering itself, but where the indexing begins. So when we describe proto-Big Bangs as occurring billions or even trillions of years before ours, that is not an appeal to an external clock. It is a way of translating the depth between segments into conventional cosmological language. The timescale depends on which proto-Big Bang segment is being described. These proto-Big Bangs can occur, evolve through full macroscopic regimes, and contribute to the geometric structure that persists across configurations. Each can generate both localized matter and energy, and distributed angular momentum in the torsional sector. These two geometric degrees of freedom do not behave in the same way. Curvature, tied to localized matter and energy, enters a strongly interacting regime, thermalizes, and is reconfigured as the system evolves. Torsion, carrying distributed angular momentum, is not tied to localized matter in the same way, and may not fully equilibrate. Across successive configurations, proto-Big Bangs generate distributed angular momentum that is carried by the torsional sector as a geometric degree of freedom. Because it is not tied to localized matter in the same way, it is not fully erased during subsequent transitions, and so it persists and accumulates as a background of distributed angular momentum. What persists is a distributed angular momentum structure carried by torsion, not something traveling through space, but something that remains as part of the geometric configuration. Then comes our Big Bang. Not into an empty state, but into a configuration that already contains this torsional background. It does not interact with something arriving. It inherits what is already there. The transition maps that geometric structure into the initial conditions of our universe. When we observe the cosmic microwave background, its structure is typically interpreted as arising from density fluctuations in the early universe. But it may not be the full story. Part of that structure could reflect inherited geometric inhomogeneity, residual torsional angular momentum. Not just matter, but geometry itself. This is not a multiverse theory in the sense of separate parallel universes. There are no disconnected domains interacting with one another. Instead, the proposal is that the Big Bang associated with our observable universe is one instance of a broader class of transitions within a single geometric domain. That domain may support multiple such events, each capable of generating a macroscopic regime, but not all persisting in that form. What we call our universe is one such regime. What persists beyond such regimes is the underlying geometric structure. The Big Bang may not be where everything starts. It may be where a particular kind of structure becomes visible. What we observe today may not arise solely from that moment, but from what the geometry retained. And just as our understanding never reaches a final boundary, but pushes the frontier one step further back, the structure we uncover may not terminate at a single origin, but extend across an ever deeper ordering of configurations. The question is not where everything began, but how far that structure extends and what persists across it. Time does not carry change. Geometry does.